How many, how many computer nerds does it take to get a presentation online?
All right. So thanks for the staff that just helped get through that technical issue. Can we get a quick round of applause for them? All right, my name's David Cheeseman. I'm going to show you how I built a covert channel using QUIC protocol headers. I'll also say this is an honor because last ShmooCon, this is also my first talk at any hacker convention. So really appreciate this opportunity. Thank you. So a bit about myself. I'm a Johns Hopkins master's student in cybersecurity. I'm a cybersecurity professional, kind of on the blue-purple team side. I was a Navy veteran, served on that submarine and on an aircraft carrier, but not that aircraft carrier. I'm also a hacker, build security tools in my spare time and throw them up on GitHub as a hobby. I also participate in CTFs, science and skepticism, home lab, gamer, maker. I just keep myself busy. So here's a quick overview of what we're going to cover. We're going to cover what a covert channel is for those that aren't familiar. We're going to cover QUIC for those that aren't familiar. Then I'm going to talk about how I built it, and then more importantly, how I evaluated it and how I Dunning-Krugered it, as well as references and a demo. So there's kind of two categories of sort of problems with covert channel. There's the confinement problem, which is where you have a process. In this case, this is a World War II era SIGTOT. It was a one-time pad teletype encryptor. And somebody from Bell Labs noticed that if he went into a different room, he could see the plain text on an oscilloscope and read it. And so this is an example of what's more commonly known as just side channel leakage. And I can't recommend enough, look up Tempest, a signal problem. That's where this comes from, this story, as well as a bunch of other stories that are really cool. But for my purposes, I'm dealing with the prisoner's problem. So you've got Alice, you've got Bob, they're both in prison for some reason. And you've got the warden Wendell here. And Wendell can pass messages between Alice and Bob. And Alice and Bob, their goal is to figure out some secret code so that they can communicate without Wendell, who can see every message and or manipulate them, from knowing what they're talking about, disrupting the communication channel that they're talking on, or even worse, manipulating the coded messages that they're talking on. So this is a very sort of useful technique for, say, journalists and also malicious actors for C2 and data exfiltration. So it's a very interesting field to kind of get your head into. In terms of evaluating how good covert channels are, how risky, year of my birth, TSEC was published by the Department of Defense, and it classified channels into storage and timing. So storage is you're storing the values directly in the data that's being sent across, or timing, you're encoding data into some time-varying signal. And they rated anything above 100 bits per second as risky, which kind of goes back to that's how fast terminals were at the time. There are more modern takes on this. Ogravi et al. Divided it into a three-dimensional classification of storage versus timing, network versus OS versus hardware, and value versus transition. And you can think of transition of, I want to encode at 3, so I'm going to take this value 2 and bump it up to 5. And then Wang et al. Proposed a risk measure that considered bandwidth not as a static value, but as a function of time. Because during the workday, when systems are live and people are using them, the side channel leakage or the covert channel that's being used may be more active and have more bandwidth than later on in the day. They also talked about weight difference, which is the sensitivity of the information. So if you have a VoIP line that has a side channel leakage and you can listen to the conversation, you listening to a Domino's order doesn't matter so much. But you listening to HR, talk about PII or something like that, that's of more value, more risky. And then they also talked about threat rate, which is the immediate risk based on bandwidth and weight difference at a specific point in time. And then threat degree, which is how much risk there is over a period of time. So 9 to 5, more risky than say midnight to 5, depending on what the channel is. So now we'll go into build it, which I built this thing because of a 2-week assignment. And one thing I can't recommend enough is throw your heart into whatever you're working on. And so this was just an assignment in my Johns Hopkins class for Covert channels. But this is the steps that I picked. First, pick a protocol. Find out if it's been done before. Do the best research you can in 2 weeks of whether or not this has been done before. Find a vector in the protocol, implement a communication channel through that vector, and then test and evaluate it. So for this assignment, I just opened up Wireshark and started screwing around until I saw a protocol I didn't recognize. And so I came across QUIC, which was proposed by Jim Roskine of Google as the QUIC UDP Internet Connections Protocol. It later got defined in RFC 9000. You'll see places say QUIC is not an acronym, but I kind of like Jim Roskine's original acronym. And basically, it's kind of a drop-in replacement for TCP with TLS, but requires fewer round-trip times to establish a connection, encryption and connection in just one handshake. And it supports application layer protocol negotiation. So most common is HTTP3, but you could do Samba or any protocol you want over QUIC. So looking into who has done research on this before, specifically around covert channels, Boran Jda did a lot of really good work on scanning for QUIC services and proposed that one could, say, take port 443 that's trusted on a network and spit up Samba over QUIC as a data exfiltration path. And his work's really good in terms of there's a lot of tools that can identify UDP ports, but not necessarily what's running on them. And he and other colleagues have developed tools that allow blue team people to scan a network and enumerate not just what ports and what IPs are running a QUIC service, but what specifically is on that QUIC service. So he actually did a talk 9 months ago called Quick and Furious. I highly recommend that you check that out. And then, let's see, do a shout out to Cooper and Will, who I talked to in the chill out room. They pointed me to this paper, so I had to add this slide like maybe 30 minutes ago. It's basically Quick Step, which is another technique to basically prevent censorship firewalls from dropping QUIC connections. So that was the research that I was able to find up until literally 30 minutes ago. Now let's find the vector. So you want to look for unstructured or optional data, timing channels, and my particular favorite, high-entropy fields, because you can hide encrypted payloads in them because they're high entropy. The connection ID is required in every header. There's a source and a destination connection ID, and it explicitly says 64 bits of entropy to be considered valid. And down below in the header definition, you can see it can go up to 160 bits. And this is a huge sort of header field to manipulate in a covert channel design. So now you got the option, all right, I got my vector, do I write from scratch or reuse? And definitely reuse if you can, especially for a 2-week proof of concept. So I use the aioquic library on GitHub, which is a Python implementation of a QUIC HTTP3 server. And then you got to find where the target field is set, figure out how it's manipulated so you don't screw up how it's managed, and then plan a protocol. So a reverse shell or a protocol tunnel would be great. I had 2 weeks, so I just did something custom. So for my message format, it's just a single letter followed by the content of whatever is relevant to that. The letter K is a keep alive because every single one of these connection IDs in my implementation, this is a limitation of it, requires that it be a part of an encrypted packet. There can't be a random CID anywhere that's random. I used AES 4096-bit encryption, and actually implemented a key exchange. Out of band would be better, but I implemented a key exchange where the public modulus is sent across, and then AES is used after that. And so you end up with this big chunk of encrypted information that you can then chop up into these connection IDs and use those connection IDs to open up connections and start transmitting encrypted data. This is a quick slide showing the entropy of random bytes versus the RSA public modulus and 512 bytes of AES encrypted data that I threw up on CyberChef. And they're all within the same order of magnitude in terms of entropy, which is critical in this proof of concept because I want this to look indistinguishable from other traffic. If the entropies are all over the place, one could determine that these connections are different because they're lower entropy, but because I met the entropy requirements, these should be indistinguishable from benign traffic. So here's a quick animation. First, both the client and server queue up their public key and start submitting chunks of them as CIDs. At any point, the client can queue up a message, in this case, a remote command, who am I? Once both public and private keys have been submitted, they can start using AES encryption at this point. The server needs to keep a queue full of encrypted data, so it just encrypts the letter K and starts sending that across. Needs to keep that queue full, keep live messages are small. Then finally, who am I is received by the server, and it queues up the response, the standard out, standard error, as just a standard message. So now we go into analysis. Bandwidth is the only one really relevant to here because weight difference would be context dependent. There's some overhead from the initialization vector and encrypted AES key. So you can kind of see in the graph how it diminishes over time as the message size, the bottom right-hand axis, grows. And as the message size grows, eventually you get a linear relationship between connection rate and the size of the CIDs you're using, either 64 to 160 bits. This is a real-world calculation I did by opening up YouTube and seeing how many QUIC connections are made with unique connection IDs. Ended up with 21. Some of them were 64-bit, some of them were a full 160-bit. And assuming I was trying to extract a 4096-bit AES key or RSA key, how long would it take me to transmit that? And so I did a rough calculation and came out to about 10.3 bytes per second, or roughly 50 seconds of me just loading pages. And that's a little bit short of the 100 bits per second, but I consider that TSEC high-risk achievement on my part. So now the Dunning-Kruger aspect, looking at your own stuff critically. An observer could notice that there's a slight statistical difference in odd versus even numbers of these CIDs. If it's perfectly high entropy data, it should be an even split. But public moduluses are always odd. And that's kind of a fringe case, but academically I kind of have to mention it. And again, this would be moot if you just distributed the keys out of band. On the manipulation side, it's susceptible potentially to AES bit flip attack, as well as man-in-the-middle attack, because right now there's no way of authenticating that public key actually came from the person that you meant it. So if somebody knows this channel's in use, they could hopefully get in there if they know where the RSA connections are, or CIDs are actually being transmitted. That's sort of a challenge on the defender's part. In terms of disruption, one could just keep a table of real connection IDs to placeholder connection IDs, but that would be very costly in terms of actually swapping those out in real time, and that kind of is antithetical to the idea of QUIC, so probably wouldn't be an easy thing to sell. Because of the limitation of my implementation, one could also just drop a connection, and that would break the encryption sync, which I have an issue for on my own GitHub on how to solve by implementing a resync mechanism. Other improvements, support out-of-order reception and sending of these connection IDs. Right now, it's all enforced in code by the server and the client implementation. And also more robust confidentiality and integrity checking mechanism, because if a bit flip attack happened, I wouldn't know, Alice and Bob wouldn't know that it had happened. And one important thing too is any of these changes can't change the entropy of the packet going across. So even just a CID, like this is chunk number 1, chunk number 2, that would lower the entropy of the CIDs going across, which would be statistically noticeable, and you could actually isolate these connection IDs have really low entropy for some reason. That's weird. Let's look into that machine and see what's going on. So some final thoughts. In covert channels, if you can find a high entropy field and put high entropy data in its place, encrypted or otherwise, it's going to be very hard to detect. And so you need other controls like endpoint protection, DLP controls, and stuff like that. Next point I'd like to close out on, just build it, even if it's been done before. I've told this to a number of junior devs that I've mentored. If you can build it and document it well, It shows your skills and your interest in a field, even if you don't have the resume stamps behind it. Also, have a healthy skepticism for your own work. It's one of the honors I have right now talking to all of you is some of the minds out here may have something I don't know. And hopefully afterwards, you can come up and talk to me and say, hey, this could be improved or that can be improved. And that's part of the fun of being in the hacking community is just learning new things. Here are some references, and I will play a demo while I take questions in the background. This is the same thing as that animation, but thanks for your time. I'm here for any questions. Anybody? Yep. So the question was, have I thought about adding padding to packets to make them more distinguishable, less distinguishable? Indistinguishable. Well, I'm only going after one specific header field, the connection ID, and that has a range from 64 to 160 bits. What's actually being used by the QUIC protocol for that particular application doesn't matter. It's similar to sort of the TCP/IP covert channels that take little optional fields that are like 1 bit and just flip the bit back and forth. But this is an entire required high-entropy header, which was why I targeted it. Any other questions? Yep. It was easy. There's definitely better encryption schemes out there. I'm just familiar with it, and there's also definitely better key exchange things. But anyway, thanks very much for your time. Have a good ShmooCon. Thanks for all the great work, last minute effort. Really good stuff. Thank you very much, sir.